So far, we have gone over how spatial data in a GIS are often split into two components: the coordinate information that describes the feature geometry, and the attribute information that describes the non-spatial or aspatial properties of the features. We most commonly see the aspatial data represented in tables, so it is referred to as tabular data. A database is a collection of individual entities stored in a highly structured way. Entities are unique objects or features represented in the database. For example, a database storing information about College of the Redwoods would have entities such as students, instructors, courses, classrooms, and grades. The term database is sometimes used interchangeably with database management system, or DBMS. This use of the term is not entirely correct. A DBMS refers to the software used to enter, analyze, search, and report data in a database. One defining characteristic of a GIS is that it incorporates the properties of a DBMS but has the added functionality of linking a database to a map. A database stores entities and attributes as tabular data. When discussing databases, a row is referred to as a record. Each record represents a single feature. For example, in a database table representing students, each row in the table represents an individual student. A single student cannot take up more than one row in the table. Furthermore, a column in a database is referred to as a field. Each field stores a single attribute type. An attribute type describes the nature of the attribute in the manner in which the database stores it in memory. These usually include numbers, strings, and dates. A string is a data type that represents text. Sometimes it is possible to import non-database tables such as Excel spreadsheets into GIS software. The GIS treats the table as a database table, enforcing the rules and structure of a database. For example, if one imports a table with the field that contains both numbers and text, the GIS will assign that field the string attribute type by default. This means that the database treats the numbers inside that field as text and cannot use them in mathematical calculations. A domain defines the acceptable values an item might take. For example, integers may be restricted to be larger than 0 but smaller than 10. Or there might be a type named color that can only take on values red, green, or blue. Tables are related through keys, one or more columns that meet certain requirements and may be used to index the rows. Given their importance, there are some restrictions on keys. For example, null values are typically not allowed to be part of a key. There may be many potential keys, or columns that uniquely ID each row, but typically one is chosen for use, called a primary key. A primary key can be composed of one or more attributes. For example, a database table about students might include 2 students, both with the same first and last name. So that information between these 2 students is not confused, the database designates a unique attribute, such as a student ID number, to be the primary key. So again, because each entity is a unique object in a database must have the mean to enforce the integrity of an entity. Ensuring only one copy of each entity prevents information from being duplicated. As we can see here in this image, we have an attribute table that has been opened up in the GIS software ArcMap. So when we work with geospatial data, GIS software often assigns a default numeric index to each record called a feature ID, or FID, which is what we normally see in ArcMap to serve as a primary key. Here we have California County shapefile. As we know, shapefiles are a common vector spatial data format that uses an index to link files. Shapefiles represent layers with a cluster of files. Each file has the same base name but a different file name extension, indicated by a suffix. So as we can see here in this slide, we have a shapefile opened up in Windows Explorer, so we could see all the different extensions. So the first kind of file we're going to talk about is a .dbf. So this is a DBase file. DBase was the first widely used database management system. It's no longer a force in the DBMS market, but they have left their .dbf format as a legacy. That's why we see that .dbf rather than something like an Excel suffix instead. So anyways, when we're looking at this in Windows and we see that .dbf, that is going to be our attribute data, or that database table. So the next type of file that you guys are probably familiar with seeing by now is the .shp. So this is the actual shapefile, and that is storing the coordinate data. So it's the feature, geometry, spatial data, so the shapes of the features defined by vector coordinates. So then we have the .shx file, and this is the index between the two. So this right here is what is giving our GIS software as a database management system the spatial awareness. So this .shx file is linking the coordinate data and the attribute data. It's linking these two guys together. So then we have that feature in a layer is going to be a record in the attribute table. So this is another good example to kind of help visualize why we, if we're going to be moving a shapefile around, we want to make sure that we're working in Arc Catalog or in ArcMap rather than in Windows Explorer, so everything stays together, because that's really important. We don't want to separate anything, otherwise not only is that link between the shapefile and the DBF file gonna be messed up, but everything else that's within that shapefile as well is going to be misplaced. Okay. Really quickly, here is the .dbf file opened in Excel. Any of the attribute queries we have done in ArcMap, we can do here as well. But we use the GIS software so we can also represent our data spatially, linking the database to the map. Okay, so queries are one of the most frequently used operations performed when working with geospatial data stored in a database. A query is a selection operation, a procedure that chooses a subset of records based on values of attributes or a set of spatial conditions. There are two primary types of selection operations: attribute queries and spatial queries. Attribute queries are different from spatial queries because they are not based on where things are located, rather on the values that are stored in the attribute table. Okay, so this is where you go into your attribute table and you select the tool Select by Attributes, so you're working directly from the attribute table, so therefore you have an attribute query. So we'll talk about spatial queries a little bit later, but a spatial query is when you're going into the search by location function, which you guys should be familiar with by now. And so that is based off of the coordinate data rather than the attribute data. Okay, so if we're looking at these two different types of queries here, we have our simple query, which is going to be just looking for one attribute, where a compound query can be looking and comparing multiple attributes. So here is an example of what it looks like when we have the window open for Select by Attributes. Attribute queries are selections based on the values of attributes. Attribute selections are commonly performed using a query builder, which is a graphical user interface, or GUI, that helps build selection operations using a structured query language, or SQL. SQL is a standard syntax, the structural rules for a programming language used for retrieving and manipulating data from a database. SQL uses logical expressions to define selection operations. Logical expressions are a sequence of operands and operators that return a value of true or false. An operand is the data value in an expression, and an operator is a symbolic representation of the process for operations performed against one or more operands. In GIS software, field name, operator, value, or string is the most basic structure for an expression. As you can see on the slide, the state name and California are the operands. Notice that California is enclosed in a pair of primes, mathematical symbols commonly referred to as single quotes. In SQL, primes indicate that what is between them is a string. In this expression, state name is enclosed in an asset of double primes, as we can see here. The GIS software recognizes that this value refers to an attribute field rather than a specific attribute. The equal sign here in the middle is our comparison operator. So comparison operators test whether two values are the same. The GIS software will check each record for the attribute California under the state name field using the expression from the previous slide. If the expression is true, it will select that record. So it's going to look at every feature and ask if it meets the criteria. It's important to know which one to use. Comparison operators are used to compare two values. And so here we have an example of some simple queries using comparison operators. So here I'm going to select the field area, and I want everything within that field that is going to be greater than 10,000. Okay, so if I put that into my SQL, it's going to select all of the areas as that are greater than 10,000. And so we could see the same here with length. It's going to be anything that's less than or equal to 20, and then with height, anything that's equal to 10, that's what is going to be selected. So I just want to talk about this really quick here because we're going to touch on it a little bit, or in a couple of slides anyways. So this not equal to symbol, you're basically telling the SQL that you're going to be selecting in the field state anything that is not equal to Colorado.